Welcome back to The Explainer. So today we're taking a bit of a cosmic road trip, about 5,600 light-years straight into the Scorpius constellation. Our destination, the incredibly dazzling, super young star cluster known as Caldwell 76, or NGC 631. Now, if you've ever looked up at the night sky and heard folks talk about the False Comet string of clusters, well, Caldwell 76 is literally the head of that entire formation. You might also know it as the Northern Jewel Box. In this explainer, we're going to dive deep into its fascinating life cycle, check out some of its most eccentric stellar residents, and ultimately figure out the final fate of this wild stellar neighborhood. Let's get into it.
Okay, so take a look at the sheer volume of cosmic traffic happening right here. This snapshot from the Chandra X-ray Observatory captures the vibrant, beating core of Caldwell 76. Astronomically speaking, this is a baby stellar nursery. The stars here are only, between 2 and 7 million years old. And because they're so incredibly young and just bursting with energy, they're pumping out powerful X-rays. That's what you're seeing is those dark, densely packed clusters of points scattered all over. It's honestly like looking down at a bustling, crowded cosmic metropolis with this massive, massive concentration of activity right smack in the city center.
But this actually presents a pretty massive challenge for us. I mean, when stars are packed this tightly together, and they're completely shrouded in leftover interstellar dust, how do we actually take an accurate census of who lives there? It's kind of like trying to count individual fireflies in the middle of a super dense, foggy forest. For decades, astronomers really struggled to get a solid head count of Caldwell 76. Low-mass stars, ones a lot like our own sun, actually, are notoriously difficult to untangle from just random background or foreground stars if you're only using standard optical telescopes. They just get entirely lost in the cosmic noise.
So to solve this, scientists had to literally change how they were looking at the sky. They needed a cosmic superpower. A research group out of Penn State came up with this brilliant new approach, comparing those older optical methods with a multi-wavelength technique. Basically, they combined high-energy X-ray data from Chandra with deep near-infrared data from the VVV survey. Think of it like strapping on a pair of cosmic thermal vision goggles. While your traditional optical telescopes get totally blocked by all that dust, X-rays and infrared light just pierce right through it. This let researchers pinpoint the young, active stars based entirely on their heat and energy signatures, completely filtering out any random imposters.
And wow, the result of that technique was an absolute breakthrough. By using this advanced methodology, they expanded the known population of this cluster to a staggering 2,148 probable stellar members. Just by looking at the universe through these different wavelengths, astronomers realized that earlier counts were missing nearly half the population. I mean, this new catalog is a full 70% larger than past census. It scooped up a massive number of those low-mass stars that were completely invisible to optical telescopes. So now, we finally have our most complete, accurate map of Caldwell 76 to date. And when you actually map out the surface density of these variable stars, it reveals something super fascinating. You see those darker, kind of pinkish-purple zones? That pinpoints exactly where the bustling city center of Caldwell 76 sits relative to its wider galactic neighborhood. It basically proves that despite the massive, sprawling size of the surrounding region, these young, volatile stars are highly clustered in a central hub. They are tightly bound together by gravity right now in these early stages of their lives. Now, let's take a tour of the local cosmic zoo, because this cluster features some absolute heavyweights. Caldwell 76 isn't just full of small sun-like stars, it's home to some giant characters. For instance, we've got Zeta 1 Scorpii. This is a massive B-type hypergiant star locked in a binary system. Then we have O-type supergiants like HD 151804, which are literally some of the hottest and brightest stars in the known universe. And amazingly, the cluster even hosts incredibly rare Wolf-Rayet stars like HD 152270. If you don't know, these are highly evolved, blistering hot stars that are actively, rapidly shedding their outer layers right out into space.
But here's where it gets even cooler. These massive giants hold even more secrets when we really dig into their X-ray signatures. By analyzing the hardness of the X-ray spectrum, the data shows that a massive 35 to 41% of these large B-type stars actually have hidden pre-main sequence binary companions. So they aren't solitary giants at all. Over a third of them are hiding smaller, younger sibling stars in the dark, siblings that haven't even fully ignited into normal main sequence stars yet. It's just a brilliant little twist in the whole family dynamic of this cluster.
Which brings us to a really fascinating quirk about those giant O-type supergiants we just met. Detailed atmospheric analysis shows a massive, and I mean massive, amount of helium on their surfaces. Now, typically, a huge star like this goes through a highly unstable luminous blue variable phase before eventually becoming a stripped-down Wolf-Rayet star. But these specific stars in Caldwell 76, they have so much surface helium enrichment that researchers actually believe they're skipping that unstable evolutionary step entirely. It's literally like a student skipping their awkward middle school years and going straight into high school. They are fast-tracking their evolution right to the Wolf-Rayet stage. No way, right?
Of course, not every star decided to stick around the neighborhood. We have to talk about the incredible backstory of a runaway star named HD 151919. This is a high-mass X-ray binary, basically a massive star paired up with either a neutron star or a black hole. Well, today, it sits a full 4 degrees away from the cluster in the night sky. And by tracking its movement backward, astronomers realized that a massive supernova explosion went off in the cluster about 3 million years ago. The sheer force of that blast acted like a giant cosmic slingshot. This binary system was literally kicked right out of Caldwell 76.
Okay, let's look at the hard data driving all these discoveries. By comparing the mass distribution of the stars with their X-ray luminosity, researchers found something super useful. The X-ray luminosities remain incredibly consistent for stars in this cluster that are under 5 million years old. And since X-ray brightness follows a very predictable pattern as young stars age, scientists can essentially use this data as a cosmic clock. So rather than getting totally bogged down in the granular data points, the big takeaway here is that this helps us age date this entire stellar generation. It confirms the median age of this bustling city of stars is right around 3.2 million years old.
So all of this data points to a really profound shift in the life cycle of Caldwell 76. The intense radiation and those massive stellar winds from the giant O and B-type stars, they've completely blown away the original natal molecular cloud that birthed them. Observations actually show that stellar winds now flow completely unimpeded for more than 2 parsecs right in the center of the cluster. The dust has literally cleared. And because all that raw material is gone, the star-forming factory of Caldwell 76 has officially shut its doors. What we're looking at now is the final product. Which honestly leaves us with this final, gripping mystery about the ultimate fate of this stellar family. Caldwell 76 is standing at a critical evolutionary crossroads right now. You see, now that the heavy molecular gas tying it all together is gone, blown away by its own giant stars, gravity has a much weaker hold on the group. So what happens next? Will the remaining mass of the stars be enough to keep them together as a permanent, gravitationally bound open cluster? Or will this beautiful head of the False Comet just slowly dissolve, with its thousands of stars scattering into the lonely galactic field forever? The dust may have finally cleared, but Caldwell 76's final act? It's really just beginning.